Say what?
Carnival.
Carnival. Oh goodness, no. That's the wrong word to use. Carnival. No, carnival is like Brazil and no. Carnival. Oh no. Sorry. In my head, there's parade, and then there's carnival. Okay. So this is more like parade, not carnival. Okay. Sorry, I didn't hear you because it didn't make any sense. Carnival. Yeah, sorry, not carnival. Alright, okay, let's have a look here. Okay. Say again?
Your same file in different formats.
What do you mean?
Like in PDF, in text.
No, these files are output of the process to change it into PDF. That does not really do anything. Okay. Right. Write it down, please. Transform. So, quite an easy lesson.
Yeah.
And in fact, a very common question on the exam. So, double good news for this topic.
This chapter is only one thing, convert from this.
It's very, very brief. Yeah. Okay. Right, so in this lecture we will study transformers. Here's an example of a transformer. This is Optimus Prime. He is leader of the Autobots, that's right. His arch nemesis is Megatron. He leads the Decepticon. Oh no, wait, hang on. That's not a transformer, that's a transformer. Sorry. So this is what we'll have a look at today, okay? Now, transformers are actually very, very simple electronic devices. So in fact, to make a transformer, you literally only need two things. You need some piece of iron shaped like this, this rectangular shape here, and you just need some wires. So on the left, you have the wire in red, and on the right you have the wire in blue. So what you'll notice here about the wires is that there's more on the left than there is on the right. Can you see that? Or I should say there's more loops on the left than there are on the right. And that's not, you don't need to draw, well you can draw this one in a little bit, Fahad. I'm just giving you the picture of it. So maybe some of you have seen this before. Okay. Right. Yeah, well first we'll get the definition and then we'll look at the diagram in more detail. So what exactly does a transformer do? So does anyone know?
It converts the current to the lower voltage something. I forgot the actual specific.
A transformer is an electrical device, obviously, that transfers electrical energy between two or more circuits through induction. But that's not why we care about it, because transferring a current between circuits, that's great and all, but the reason we really care about transformers is because commonly transformers are used to increase or decrease voltages.
Yep.
So electromagnetic induction provides a electromotive force across a conductor which is exposed to a magnetic field which is changing. Commonly, so actually maybe I should have put that in red. Commonly, transformers are used to increase or decrease the voltages of alternating current in electrical power applications. So in other words, for me a transformer is a thing that changes the voltage. And have transformers at home. So do you see this here on my laptop? See this here? Everybody look. You all know this part of your laptop? Okay, this is the transformer, I believe.
Yep.
So the voltage comes in at 220 and then exits the transformer at about 12. Your phone, does anyone, you see here, Tekken, the phone charger behind you. You don't need to take it out. But there's a transformer in that.
Just one thing there?
Yeah, they've gone quite small nowadays. So my sounds so old. My phone chargers when I was a boy, they were really big plugs. Okay, like really, really big, heavy plugs. Now they're actually the size of a regular plug. Okay. So transformers, you can make them quite small nowadays, like the one there. Anyone else got one? You have your laptop with you, and it has the box part as well. Okay. So they come in all sizes now.
I remember when the Nokia set, the heavy set is this much of that.
Yeah. No, I remember like big, heavy, fat plugs, really heavy. Yeah. I don't. Sometimes you might see an old router with one of these big plugs on it.
Even I've seen that, that one converts 220 to 110, 110 to 220. This much.
Yeah.
In Pakistan we used to have.
Yeah.
But sometimes the machines we have from Saudi, it's like 110.
Yeah. They convert it.
Yeah.
Okay. Did you write this down?
Yes.
Yeah. So transformers are very, very important devices because every device requires a different voltage. So my laptop, I don't know, probably needs about 12. The smartphone probably needs about 6. What else do we have here? Other things like the projector and the fan probably are fine at 220. The light bulb, I say, is fine at 220. What else have we got in here?
Maybe?
I think 220 is fine for that.
Projector.
Usually, the thing that needs a lower voltage is electronics like smartphones, laptops, tablets. These need a lower voltage. Okay. Transformers can be used to decrease the voltage and increase the voltage. So, if you want to increase the voltage, we use this adjective step up. We have a step up transformer, means it'll increase the voltage. And if you want to decrease the voltage, well, no surprise, we call it a step down transformer, a transformer that decreases the voltage. Yeah. Continue?
Yes, please.
Yeah. Right, so let's go back to the picture and let me draw it. Right, so first we have a piece of iron cut into this kind of rectangular shape with a hole in it. And then what we have is be careful. Then what we have is a wire wrapped around it. And then on the other side, a wire wrapped around it. There's N1 loops here and N2 loops here, and these are different. They'd be pointless if it was the same. This side here we call the primary side, and this side here we call the secondary side. And there's an AC supply here with voltage V1, and then out comes this side an AC supply V2. And if you want to put in simpler English, this is like the input and this is like the output. Usually made of some kind of iron, soft iron or some conductor like this.
This is decreasing the voltage in this picture. In this picture, this is decreasing the voltage, right?
In this picture, it is decreasing the voltage.
If it's other way around, so the right side going to be primary, this is going to be secondary.
No, well, we'll talk about the change of the voltage in a moment, but in this picture, this would be a step down transformer.
Do I need to know that?
Or wait, or is it step up actually? Hang on, let me think for a second. V1 over V2. No, it's a step down, yeah. We'll get to the reason why it is what it is in a minute.
What's N1 and N2?
Huh?
N1 and N2. N1.
Oh yeah, sorry. N1 is the number of loops here.
Okay.
So N1 loops or windings. N2 loops or windings. Okay. Got that? So, a transformer changes the voltage. Let's explain how it changes. So let's imagine we have our current coming in here and going out here. Oh, sorry, are we ready for the explanation? Yeah. So you remember from the start of this chapter the right-hand grip rule, that when we have a current moving in one direction, it produces a magnetic field. By using your right hand, you can work out the direction of the field. So if the current was going from me to you, then my right-hand rule says the magnetic field is going around this way, around the current this way, clockwise, for me. So the current that's heading from me to you, the magnetic field is in a clockwise shape around the current. So that means around this here there is a current. And what we would like to do is make, okay, so actually let me draw the magnetic field. Do you remember Lenz's law that says the magnetic field, well, what's Lenz's law? Remind me. Yeah? That's it. Lenz's law says the magnetic field will be in the opposite direction of the voltage. So here, which way should I draw the magnetic field? Well, I think, the current is wanting to go up, isn't it? So the magnetic field is wanting to go down. So there'll be a current, or it's not current, sorry, a magnetic field going around this way. Will this make a current in this? Yes or no?
Yes.
By what rule?
Uh,
By the rule we did in the last class. Why?
Second one? Second law.
Which is called... guys, come on, it was like 2 days ago.
No, 2 days ago, it was weekend.
Yeah. Go on, Chuck.
Make it show next page,
So there is,
Faraday's law of induction. Right? Which I do wonder if that was literally the last lesson. Lesson 6. Induction, yes. So congratulations, you have forgotten literally the last lesson you have learned in physics. Oh well. Not me taking the test in the summer. So, Faraday's law of induction says there should be a current in the second wire if there's a magnetic field going through it. Well, not quite. Faraday's law of induction says if there is a change in magnetic flux. In this picture, or in my description so far, the current is direct and the magnetic field is direct. But if we alternate the current, that is, if we switch it from going forwards to backwards, keep changing it, then what we'll get is the magnetic field will change directions. So if the current is going up, the magnetic field will go down, and then when the current switches and goes down, the magnetic field will go up. So we have a change in magnetic flux. This change in magnetic flux will cause the current here to appear. And in fact, for example, when this is going down, the current will be going up. So when this is going up, the current will be going down, and this induced current will be going up. So let's work out a formula here. So, there is going to be a change in flux through this iron core. So if you look at the left, voltage 1 equals minus N1. But I don't care about the minus because I know the direction. So I'll just drop it. Although if you leave the minus in, it doesn't matter. N1 over change in flux over time. And on the right, you'll have voltage 2 equals N2 change in flux over time. These are both Faraday's law of induction.
always N2 less than N1?
N1 not equal N2.
Yeah, I know, but always N2 less than
No,
N1?
just not equal.
Just not equal.
Now, if we just look here for a moment, notice please on the left, what is the thing that you are providing in the formula? Or what is the thing that you're doing? Well, yeah, you are causing a change in the, I suppose you might say that you are providing the voltage to cause, you're providing an alternating current, a voltage here, and the cause is you're changing the flux, the magnetic flux. On the right hand side, the difference is this is being provided because it's coming in from the left, and then the cause or the result, maybe I don't want to say cause, I'll say result. So the difference is on the right, the result is you get this induced voltage from providing this alternating flux. On the left, you provide a alternating current, and you get the change in flux. So what I'm trying to say is that is the same on both sides. The only difference is on the left it's the thing that you're making, whereas on the right it's the thing that you're getting. but they're still the same because it's one magnetic field. There's not two magnetic fields. So, we can then equate these equations. We can say change in flux over change in time is V1 over N1, and then here change in flux over change in time is V2 over N2. And you might decide, okay, well I can make these equal. So V1 over N1 equals V2 over N2. And a little bit of a rearrangement. The voltage in the primary coil over the voltage in the secondary coil equals the number of turns in the primary coil over the number of turns in the secondary coil. And this is our formula, which I'm sure some of you have seen before.
Stephen,
Yeah.
here, V1 and V2 are equal, isn't it?
V1 and V2?
Yes.
Oh no, they're different. Yeah. You see, Carrara, if the N1 and the N2 are different, then the V1 and the V2 will be different. That's why at the start I said the N's are different. In a sec, yeah. Another thing to note. A transformer does not provide energy. It only changes the voltage. But you know that power equals IV. Now, if the transformer is not changing the power or the work done, then the increase in the voltage must come at the price of a decrease in the current to keep the power the same. You can't just increase the voltage and make free power. So the current has to decrease. So what you could say here is, well, then that means the power in on the left must equal the power out on the right. That means I1V1 on the left equals I2V2 on the right, which means I1 over I2 equals V2 over V1, or rather I2 over I1 equals V1 over V2. So what I can do is I can use this result to make a second formula if I like, by putting it in here. I can say I2 over I1 equals N1 over N2 as well. And it's not really a formula, but I think it is worth remembering that the power that goes in equals the power that comes out, as long as the transformer is 100% efficient. Most transformers are actually quite efficient. Like Tekken, if you put your hand on that plug there, put your hand on the plug. Yeah. Is it warm? Only slightly, yeah? Not much. Not like the projector. If you put your hand on top of the projector, it's probably quite warm. Not warm?
Okay.
Oh yeah, the heat's blasting out the side here. So transformers are quite efficient. So yes, all of this please. What's that now? What's that? So explain to me why a transformer would not work if the current is direct and not alternating. Why would it not work?
So direct.
KJ first. He's half asleep. He needs to talk or he'll fall asleep. What is it?
Since the current can't change, you can't increase the voltage, you can make free power.
No. Nice try though. Fahad?
Direct current, because direct current don't change its direction.
But that's the definition of direct. No good. Faraday's law of induction says you will induce a current if you have a change in magnetic flux. Right-hand grip rule says that a moving charge will produce a magnetic field. If the charge is constant, the magnetic field is constant, therefore not changing, therefore no induction. So, just to be very clear, if you have a direct current, then you will get your magnetic field around the current. But this magnetic field is constant. So that means the change in the flux is equal to 0. So that means then if you put a conductor near this magnetic field, the voltage will be 0. There will be no voltage because of Faraday's law. So what you could do is then switch the current back and forth, changing it from clockwise to anti-clockwise. Then the change in the flux will not be 0. It's changing. It's going positive, negative, and so the voltage induced will not be 0. There will be a voltage. So it doesn't work with direct current because with direct current you have no change in the flux, and the reason there's no change in the flux is because direct current, the magnetic field just continues in the same direction forever as the current. You need to have something changing. So this is why transformers don't work with direct current. It needs to be alternating current. Okay? They asked this in the exam a while ago, I don't remember when. They said, explain why a DC current would not be suitable for a transformer, would not work in a transformer. Okay? So this is the reason why. Now, we need to be doing revision at home because you forgot the stuff you did in the last lesson, which is not good. Not good. Okay, let's continue then. So now, yeah, in this picture the current is starting coming in at the top, so then it goes, flux goes up. Is that what I drew? No. Oh, rats. I drew my flux backwards. I should have, at the start, yeah, rats. When it was coming in this way and leaving this way, it's going up, which means the magnetic field is going down. So it's like around like this. Yeah, I drew it backwards. So sad. Oh well, that's life. Okay, so we have this formula. And because of this formula which I gave you, we can also say this. So you wrote all of these down, haven't you? Yep. Okay, let's have a look at our first question. So write this one down.
Multi-question swaps?
Yeah. Got the question?
Interesting.
Yep. Yep. Okay, so inside this little toy is a transformer to change the high voltage to a low voltage. So you don't have to draw it, but what's happening here is in from the mains power supply of the home is 220 volts, and then the toy runs off of this. In the question I said how many turns were here? 4, what is it?
4,400.
Okay. And what voltage would you like here? 9 volts. So you have, is it 6? Okay. So you want to play your Game Boy here. Come on, you know what this is. Right, so here you have 6 volts. So V1 over V2 equals N1. What's N1 here? 4,400, was it? 4,400 over N2. So then N2 would equal 4,400 multiplied by 6 over 220. So then N2 is 120 turns. Simple, yeah? Alright, let's have a look at another one. Can I go back? Yeah. Oh, no, sorry. Too simple, I decided one was enough. Okay. So, what we can do is, I can let you, they're very, very simple. You could do them now in like 5 or 10 minutes. I don't even think it would take 10 minutes. 5 minutes. And then, huh? Oh yeah, no, take your time. Like, I'll give you a few minutes to do this, and then I'll do them on the board, and then that way this lesson is finished. Then in the next lesson we can start something new, and for the rest of this class, we can look at some exam questions then, okay? We can see what this looks like in the exam. We could have a look at fields in the exam. Alright, can I put the light on, or do you need to keep still seeing with it? Do you want to take a picture on your phone, or?
That's good. That's good.
That's good. No. I'll just stop the recording.